Hi, everybody. Welcome to week 5. So this is kind of an exciting week because we're going to look at decision tree classification, which is we looked at k-nearest neighbor last week, and it is a very kind of simple idea. It's a very powerful classifier, but it does have some issues, most notably the time it takes to classify new items. But it's also kind of disappointingly simple in the sense that it doesn't really try to form a theory of the data. So decision tree classifiers do try to form a theory of the data, and they have a different package of strengths and weaknesses that go with that. So this is the first real learning algorithm, in a sense, that we're going to be looking at, the first one that really tries to learn something about the data. It's also the first time we're going to use sklearn in Python. So we're going to, instead of coding this one from scratch, which is a little bit of a daunting task, we're going to use an off-the-shelf plugin. So we're going to get to take a look at sklearn, which is the package we'll use in Python, and how that works for classification. So I think there's going to be 2 videos this week. In this one I'm just going to look at the basic idea of decision tree classification, the kind of the theory behind it, if you will, lightweight version of the theory behind it. And I'm going to leave you with an activity to try, a paper and pencil activity to try on your own, and we'll debrief that in class. And then in the next video, I'm going to introduce sklearn. We're going to do a bit of coding, and I'll show you how the code works in Python to create a decision tree classifier and display it. Okay, so if you take a look at the handout, which is up on my screen here, what this does is it walks you through an example of a decision tree. But I thought what I would do is walk you through a slightly different example. So same data, just a different set of training items. If you look at this data set here, it looks very similar to the one that's on the handout, but it's a different set of blue and red X's. So this is from the famous iris data set. It's flowers again that were measured, and then it was used to classify them into actually 3 categories. I'm only doing 2 categories here. Red is setosa irises, and blue is versicolor irises. That's 2 different species, I guess. And I'm only using 2 measurements here of the 4 measurements. So I've simplified the data down. So we're doing sepal length and sepal width. I'm not sure what the sepal means. I should have looked that up before. You guys can look that up. It's something to do with a leaf measurement or something like that. So length and width of some feature of the plant. And you can see that it clusters pretty nicely, actually. You could draw a straight line through it right here. But that's not what decision trees do. Decision trees do something a little different. And do keep in mind that this is a toy example, in the sense that data in the real world won't cluster as nicely as this in 2 dimensions. Okay, so the decision tree algorithm, what it does is it's a recursive, greedy algorithm. It looks at each step, it takes a look at the data that you've given it, and it tries to find a straight line in the data. So it looks through all the feature values for sepal width and imagines, drawing a straight line at each of those places. So it imagines a straight line here, imagines a straight line here. Those aren't very straight lines. Whoopsie. Still getting used to my device here. Imagines a straight line here. So it tries all these different cut points, and it looks for the best one. And the best one is kind of defined mathematically, but you can think of it just as the place where you get kind of the purest division on each side of the cut. So it'll try all the cuts that are horizontal, and then it's going to try some vertical cuts like this through the data. So one there, one there. It's going to try a lot more cuts than this. But again, it's looking for the best looking split, the best way to split the data into 2 relatively pure groups. So it searches through all the features. We only have 2 features, length and width, but you have to imagine this happening, if you can, in a multi-dimensional space. And it's going to try to find the best cut point. So I want you to look at this data now, and what do you think is the best cut point for this data? I have my own idea of what the best cut point is. You might have noticed I've purchased myself a new input device for just so I can do this, but I'm still getting used to it. So it's a pen tablet. You can't see the tablet, but so take a look. You could try different vertical cuts. I'm going to go with one here. I think that's a pretty good cut Because if you can see the way I'm moving my mouse, it will leave a couple of bad unclassified points above, a couple of wrong. If you imagine, take a look above this line that I'm drawing here. The imaginary points up there, the data points up there are mostly red and not very many blue. And then below it, they're mostly blue and not very many red. I could also try maybe a vertical cut point. Let's try this over here maybe. Something like that. A cut point like that would leave everything to the right of it is correctly classified. It just gets one classification. So at that point you're finished, because anything to the right of that line you can just classify as versicolor because they're all blue. But then to the left there's more work to be done. Okay, and which of these is better? I mean, it's hard to say. And it's sort of for us eyeballing it, it's just kind of a judgment call. The machine has a specific measurement in mind that it can do to decide. I'm going to choose this cut because it leads to a slightly better, more interesting tree, even if maybe it's not the best. So I'm going to try and do this here. There we go. There's our cut line. So that's our first cut. Sorry, it's a bit crooked, but you get the idea. And it's happened at a width of, looks like about 3.2. So what you can do is you can go over to where you're building your tree. Let me just put and this is the first question. This is the first node in our decision tree. So the first question we ask when we're classifying is the length, I'll just call it L, greater than, or you could do it as less than. Is it greater than 3.2? Okay, so that represents this horizontal line right here. And there's two possibilities, either yes or no. So let's draw some lines out here like this, and we'll say right here we'll go that this is the yes line. Okay, so to the left is yes, and to the right is no. Okay, so if it's greater than 3.2, let's deal with the yes side first. Greater than 3.2 means we're out here. Okay, so we've divided the data into two halves, and in the algorithm we would partition the data around that line, and then we would recursively call our algorithm on each side of the line. So we would first maybe starting with the left-hand side, we would say, okay, for this data, are we finished up here? Is this data now pure? Could we just say this is setosa or this is versicolor? And the answer is no, because there's a couple of misclassified points. So we have to draw another line, which we can put wherever there's a lot of room to put it. You can see the line's going to go kind of like here, and that will actually finish the task. It will, for this side, it will divide the right-hand side of that line will be all blue, the left-hand side will be all red. So let's go ahead and just do that. So from right about here, oops, I accidentally drew it in red. Let me do that again, and I will draw it in gray. So there's our line. And it's only splitting that side of the data. We're only working on the left side of the data now. So then over here, we have to ask another question. And this is to do with, oh, I'm so sorry, I got this one wrong up here. This should be the width. Can I edit that? It doesn't seem so. Okay, I'm going to delete that. And I'm going to put another one down here. Should be width greater than 3.2. Sorry about that. There we go. We'll leave that there. And then over here, so that was the sepal width, not length, greater than 3.2. And the answer was yes, and we're out here. Now we want to do the length. So I'll just put that as L. And it looks like the cut point there is maybe about 5.9. So the question that we ask down here is the length greater than 5.9? And there's going to be two possibilities for that as well, yes or no. Pardon my scratchy lines here. And with the left-hand side being yes, like before. Okay, so let me move this up. Alrighty. So let's take a look at this left-hand side here. That now we recursively call the algorithm on the left-hand side, which is greater than, actually it's a bit confusing because the left-hand side of the tree here, yes, it's greater than is actually the right-hand side of the data. It's this data over here. If it's greater than 5.9, we're in this data. And at this point, we actually hit the stopping condition, the default stopping condition of the algorithm, because there's no work to be done here. All we have to do, if we're in this area, we can just say it's versicolor. So I will add that down here, versicolor. That's the classification we're going to go with if we end up here. And on the right-hand side of the tree, which is the left-hand side of the data, because over here we're less than 5.9, the answer down here is setosa. There's no work to be done. It's just setosa, like that. So we've finished the left-hand side of our tree. First question we ask, is the width greater than 3.2? If yes, we're up here. So we ask, is the length greater than 5.9? If yes, we answer versicolor. If no, we answer setosa. So we're forming a theory. And we're also forming a theory of the data that can be understood by a human being, which is one of the great advantages of decision trees. A lot of systems like deep neural networks, even k-nearest neighbor, don't really lead to much insight into the data. They don't give you a really good theory. K-nearest neighbor just says, if you ask k-nearest neighbor, why did you say it was setosa? It'll say, well, because it was close to these other setosas and not as close to these versicolors. That's the only reason it has. It's not really a theory. But here we can say, why did you say setosa? Well, because the width was bigger than 3.2 and the length was bigger than 5.9. So that categorizes setosa. That's like a little micro theory of setosas. Okay, we're not quite done though. We hit the stopping condition here and here. Now we need to do the no side of the tree over here. So is the width greater than 3.2? No, it's less than 3.2. So we're down here and we're almost done. We can see where the line needs to be drawn over here. Let me just do this little trick. So I'm going to put my line over here. Okay, and I will go there and I will just go right there. So that's about 4.7. Let's call it 4.7. Looks like about 4.7. So I'm going to go over here. I'm going to go, is the length greater than 4.7? There's no particular reason why I'm choosing greater than, by the way. It was just an arbitrary choice. You could ask the question, is it less than 4.7 here as well if you want. And you have a yes side and you have a no side. And I will just label one of those to be the yes side so that we can be sure what's going on. Whoops. Let me move that over. There we go. And then again, like before, we've actually finished. If the answer is yes, we are over here. Again, it's a bit confusing because the left side of the tree is the right side of the data. So if we answer yes, then we are in versicolor land. So over here we go versicolor, like that. And if we answered no, we are over here in setosa land. So we answer over here setosa, like that. So that then is our final tree, and this is what the division of the data looks like. So each one of these questions works on a different subset of the data to divide that data in two by drawing a vertical or a horizontal line in the data. Okay, so that's basically how the algorithm works. Now there's a bit more to it than that. Beyond that, there's a bunch of parameters. We could also say something about how the computer makes its decision about which is the best looking cut. That kind of delves into probability theory or information theory, which is a little bit beyond the scope of what we're doing here. Just suffice it to say that there are a couple of different mathematical ways to decide what's the best split. And there's a lot of implementation details. Because if you can imagine, you're searching this huge space, and even here, there's so many different cut points you could choose here and here. It's going to have to consider a lot of possibilities because there's no way for it to tell ahead of time. And now imagine that there were 100 features or 1,000 features, and that the ranges, and that there were 10,000 points that you have to choose cut points between. This is one of the smaller drawbacks of decision trees, is that the learning phase is very slow, but categorization is very fast. Because even if this was an enormous bushy tree, 20 steps deep, to travel through the tree is really fast. To travel through this tree takes two conditionals. So you have to ask, it's basically 2 if statements to get through the tree. That's super fast. Even if the tree had a million things in it, a million different leaf nodes down here, it would probably only be about 20 or 30 steps high because it logged to the base 2 of a million. So 20 or 30 if statements it'll go through in a snap as well. So it's going to be way faster to categorize things once you have your theory, way faster to categorize things than k-nearest neighbor, which has to compare each new incoming input to every other input that it's got in the system. Way faster to categorize, but way slower to train than k-nearest neighbor. K-nearest neighbor has no training. You just give it the data and it waits, doesn't do anything until it's time to categorize. This one does really all of its hard work up front. So it does all the training first, but then when you deploy it, it can categorize really, really fast. So and you also get a nice human readable theory out of it for what's what. Okay, so this you should read over this. This goes through another example and see if you can follow this tree here. So we end up with a slightly more complicated tree here. So see if you can follow all of the cuts that were made here and make sure that this diagram over here makes sense given this diagram over here. Okay. Now this tree and the one that I just drew for you, they both achieve 100% accuracy on the training set. But then there's an open question about how well they're going to perform on the testing set, right? So imagine unseen data. It's made some pretty rough cuts here. If we had more data, we may find that blues go all the way up to here, and it's made the cut in the wrong place. So it's going to be important how much training data you have and how representative the training data is. It's also possible that when you drive to 100% accuracy on a data set, on a training set, that you will overfit. We talked about that in an earlier class, that you will fit the idiosyncrasies of the training set and miss some crucial generalizations. So anyways, pros and cons. Big pro, interpretability. Machine learning methods are often accused of being black box methods, meaning they produce answers that seem to be reasonably accurate, but you have no idea how they're producing those answers. There's been a lot of discussion recently in the last few years around how systems that are used for domains as diverse as categorizing or predicting who should be treated in an emergency room situation and who should not be treated right away, like how to prioritize the order of people being treated, how to kind of triage them. That's one type of system. Another one that I saw was, I think it was Google, might have been Facebook, that were trying to come up with a system that would learn to read people's LinkedIn profiles and resumes, CVs, and make some predictions about who would be the best hire. And what they found is that these algorithms are picking up on markers of race and sex, and actually reproducing discriminatory outcomes because of the kind of data that they're being fed. So they were learning to unfairly discriminate against, in the medical example, against people of Black and Latino heritage, and in the case of hiring for high tech, they were discriminating. The algorithms were discriminating against women, and this is because you give them a whole bunch of data, and they learn the biases that are already in the data, and that can be really damaging. So one of the maybe the good things about having a theory that you can then look at is that you might be able to see the biases that it's learning, and you might be able to try and correct it. In some cases, these biases can be corrected, and in some cases they can't. So the high-tech company that was trying to come up with a good hiring system eventually scrapped their efforts because the data that was out there was just inherently biased, because there are fewer women in tech, probably because of systemic sexism. Because of that, they were unable to find a good way to tweak the data and arrange the data so that bias would go away. No matter what they tried, the system kept learning that bias. Okay, feature selection. So imagine you have 1,000 features. You could form a tree that picks only a few features. And that's kind of important because in k-nearest neighbor, we didn't talk about this that much, but if you have an irrelevant feature in there, you're using all the features for your distance calculation. You're using all the dimensions of the data, but you might have a few totally irrelevant features in there, or features that are actually working against you because you don't know ahead of time what's important. And the k-nearest neighbor will just go ahead and use those features anyway, and it may not be as accurate because of it. But for a decision tree, at each point it selects only one feature, and there's no reason for it to use all the features. So if you have 100 features, it may end up only using 5 or 6 to categorize all your data with a high level of accuracy. And then you've learned something about your data too. You've learned which features were the most relevant for classification, and you don't have to worry about putting in features that may not be relevant. You can put them all in and see what the classifier does with it. The other pro, it's fast, very quick to categorize new examples. So once you've got your tree, it's super fast categorization. And you don't have to normalize the data like we did with k-nearest neighbor. With k-nearest neighbor, because of the distance calculation, if you had one feature that was scaled really wide compared to another one, that the feature that had really high values is really going to skew your distance measurement, and it's going to essentially exaggerate the importance of that feature. Because we're just choosing cut points in the data, it doesn't matter whether in this case, whether the data goes from 0 to 1 or from 10,000 to 1,000,000. It's going to find, it doesn't matter if you scale it or not, it's going to find the same cut points. So a lot of pros, a lot of things going for decision trees. Here's a con. You tend to get, on a small training set, like the ones that we were using, there were places where we had a huge swath of possibilities. So over here, like right here, there's a lot of places I could draw that, and we might want to collect some more data to get a better sense of where the right place to draw this cut line is. So a small data set is going to work against you in decision trees. You're going to get a higher error rate, and it's also going to be slow for training. So it gets exponentially slower to train as the data sets get bigger, more data, more features. Okay, here's the learning algorithm. If you wanted to sort of, try and implement it on your own. Imagine we have a create tree function. This is written in pseudocode. It's not in Python. Where we give it a two-dimensional array of data and then a one-dimensional array of the labels that go with that data. What we do is first, this is our stopping condition. If all the items in the labels array are the same, so if everything's versicolor in this data set, then return a tree node just containing that label. So you return a tree node that just has the label versicolor. Or maybe there's not enough data. That's another possibility. Maybe there are other stopping conditions, other places where you might want to stop. So you might decide that, there's only 2 data points here. One of them's versicolor, or there's only 3. 2 are versicolor, 1's setosa. Do I really want to draw that cut line, or maybe I should stop here to avoid overfitting, in which case it would go with the most frequent label and just return a tree node. But in any case, there's your stopping conditions. If you decide that you're going to do a cut, then you have to, and this is, there's a lot of work in this one line here, find the best cut point using some feature f at some value v. So you're going to have to search through all the features and all the values and figure out what's the best cut point using some measurement. So there's a lot of work wrapped up in that little one line there. And then you create a new tree node that represents f less than v, or I was using f greater than v, doesn't matter which one you use, it's your choice. And then you divide the data into yes data and no data. So you go through all your data points in here, and anything that is true on this feature value for that data point is less than the value, you put it in the yes data, and if it's false, you put it in the no data. And then you divide the labels the same way. So you end up with yes data and yes labels, which are related arrays, a smaller data set, and no data and no labels to represent the left and the right side of the tree, the yes and the no side of the tree. And then you you create your node n. Imagine a tree node. It might have a left and a right link. So then you assign to your left link the result of creating a tree with the yes data, and you assign to your right link the result of creating a tree with the no data. So these are the recursive calls. So we recursively call create tree on the smaller sets of data. We work on the left side first and then the right side. and we end up with a full tree definition starting at the current node n. Then we just return that node, and we're done. Okay, so that's how it works. That's how the decision tree learning algorithm works at a very high level. And you can see at a high level, it's recursive and it involves trees, so stuff from data structures. So it's not novice level code by any means. But the basic idea, if you understand recursion and you're familiar with tree structures, is a pretty simple idea. All of the difficulty, the real difficulty beyond, there's coding challenges in all of this stuff in doing things efficiently. But the theoretical challenges involve finding the best cut point and knowing when to stop. Okay, so by default, sklearn and our simulations that we did, we went all the way to 100% accuracy on the training data. But we've seen in the past why that might not always be the best thing to do. And that brings us to the activity, the unplugged activity that I would like you guys to try before class and bring your solutions with you. So how are you going to do this? Well, if you have an ability to, if you have a paint program or something, and if you have a tablet like I've got, you might be able to scribble on this by taking a screen cap of it or something. Or you might want to just print it and then just draw with a pencil if you have access to a printer. It would help to have a color printer though, unfortunately. Sorry about that. When I do the class live, I print these with color printers, and then I bring them to class to give to the students. But what I would like you to do is, on your own, simulate the process of a decision tree. So try to figure out, where are we here? Here we are. Where are your best cuts in this data? Look for horizontal cuts, look for vertical cuts, and try to find ones that result in relatively pure lefts and rights. Now this is the banknote data. So if you remember, the banknote data is a hard set with entropy and kurtosis. It's the similar set to before, but I've greatly reduced the number of items in it to make it a little bit easier to kind of visually see. But you can see that it's still pretty mixed up. There's an X right here in the middle of the greens. There's an X over here in the middle of the greens. There's a decision tree algorithm. If you just keep running it, you can make smaller and smaller and smaller cuts until you have pure areas everywhere. But again, that might not always be the best thing to do. So I want you to think about what does the best split look like? Do you have a rule of thumb that you're using, or are you just eyeballing it? Or can you come up with some rule of thumb about why this split is better than that split, for example, or why this split is better than this split? Come up with some reason to believe that. Maybe even write it down. And the second thing you want to think about is, when do you stop this process? So when do I stop splitting? Do I go all the way to purity, or do I have some other criterion of stopping? And what would that stopping criterion look like? So I'd like you to try that. There's a little bit of debrief stuff down here. Don't look at that yet. Just think about it on your own and try to create a decision tree. So you'll draw the cuts and then write down the node at each step until like I did, build the decision tree as you go. And then take a look at this stuff, and we will take it up in class, and we'll go over this example in class as well together. Okay, and we'll discuss the issues. In the next video, so I would like you to try that actually now. In the next video, which I would like you to wait until you've at least tried this activity, we will look at sklearn and the decision tree code that's built into there. And we'll take a look at some of the parameters, some of the ways you can tweak it, and they all revolve around how you make the split. Well, most of them revolve around how you make the split and when you stop. So those are the main ways to tweak the decision tree learning algorithm to try and get better performances out of it. Okay, so I'll see you in the next video, and good luck with the activity. We will take up the activity and do the debrief next class, and I'm hoping that will, in the live class I mean, and I'm hoping that's going to tie everything together, the code and the theory together when we do that. But it'll help a lot if you've tried the activity on your own. All right, see you in the next video.